All right, so we now have a smarter way to figure out if a number is prime or not. The idea is very simple using mathematics. We know that if I check until square root of n, that is in fact sufficient. But for Python's sake, I need to have a plus one here so that square root of n is in fact included as we just saw for 25. So, this is now a correct algorithm. This is an efficient algorithm as well. But let's see how efficient this is and where exactly is efficiency coming from. Can we quantify that? So here I am running this for the 8-digit number. Remember previously this determining this prime number took us approximately 0.65 seconds. When I run this now, it takes 0.0004, so significantly less. You know, clearly much more, let's say, efficient. But remember, when we ran this for a 10-digit number, the simple, let's say, the naive algorithm. So I'm going to get to a 10-digit number. So that I guess is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So that is 1 7 zeros. Oh, sorry, 1 8 zeros and 9. So that is definitely a prime number. When so I get to my large 10-digit number. Remember, this took approximately 70 seconds to run. When I run this now, magic, right? This runs like in absolutely no time, 0.005 seconds. Really fast, right? So clearly our smarter algorithm is much more efficient, in figuring out the prime numbers compared to the naive algorithm. Let us try to quantify what exactly is going on. So like I said, the run time in the previous run came down from about 70 seconds to say 0.003 seconds. Dramatic improvement. Why did this happen? Well, think about it. Let's take a 10-digit number. Square root of that is say 31,000. So what does that mean? Remember, our loop is running n times approximately. It means that our naive algorithm was doing 31,000 times more work than what was needed, which means it was running the loop 31,000 times more than what was actually needed. And hence it was terribly inefficient. Remember, one good way to look at, let's say, efficiency is this question: is my algorithm doing more work than what's actually needed? In this case, the answer is yes, and very badly so, because 31,000 times more work was being done when it was actually not needed, did not add any value. And clearly the effect is seen. We see the runtime dramatically coming down, right? So this is kind of concluding our, let's say, the first problem that we looked at, which is to find a prime number. We started with the naive algorithm. First thought, correct, that's good. Not very efficient. So we think of, let's say, better solution, and we come up with a better solution, which is dramatically more, let's say, efficient. The reason is this is now scaling not as n, but in fact scaling as square root of n, and square root of n for a large n is significantly smaller than n itself. And that's exactly what we are seeing here. In fact, the theme of this problem is a recurring theme we are going to see in this course. Think of an algorithm and then think of its efficiency. Try to reduce the way the algorithm scales as n increases. And we'll see this again and again. This video is a part of the Algorithms and Olympiad track at YByte. Look at our website www.ybyte.in for more details and enjoy coding. Take care. Thank you so much. Bye bye.